One of the early organizational schemes of the elements was done by Lavoisier in the late 1700s. There were 23 known elements at the time. As more elements were discovered, there became a greater need for the elements that we had identified to be organized in some meaningful way. The first successful organization was published by Dmitry Mendeleev in 1871. He organized the elements in rows by increasing atomic mass. When he came to an element that had similar properties to an earlier element, he started a brand new row. Our current table is his table, but on steroids because it's a whole lot bigger. It's better to think of our current table as organized by increasing atomic number versus increasing atomic mass. Each element will have one more proton than the element that precedes it. So our atomic numbers increase sequentially as we move from the left of the periodic table to the right, and from the top to the bottom. Because the periodic table contains so much information, it's sometimes useful to block it off. And we can block it off in a number of different ways. This video will walk you through some of the more common ones. Behold, our periodic table. Now it's famous, but really it's just a table, so it has rows and columns like all other tables. The chemist is going to give these rows and columns fancy names, though. We refer to the rows as periods and the columns as either groups or families, with group being the official name. We also number both the rows and the columns so we can find things faster. The period number scheme is pretty straightforward. We start with the hydrogen helium, the short row on the top, give it the number 1, and then number straight down the table. The only trick is remembering that the two rows that are included below the table are actually just a subsection of rows 6 and 7. La, or lanthanum, goes directly behind Ba, or barium, on the 6th period. It just makes the table kind of dumb-shaped to do that because you have to shift everything else over to the right, and so these generally are pulled out and placed below the table. Now the numbering schemes for our groups are a little less straightforward, and yes, there's more than one way to do this. Now the newest scheme just numbers them straight across 1 through 18, and that seems easy enough, but a lot of chemists feel that our older numbering system was a better way to take care of our elements. Now that system numbered the tallest of our columns 1 through 8A. Now these groups largely made up the original table, but that's not why they get the A's. They have pretty characteristic properties and they behave relatively uniformly, so they're generally considered separately from the rest of the table. Now the elements in the middle of the table got numbered using B's. This scheme does a better job of isolating what the elements that do what we want them to do most of the time, or those A elements, from those harder to work with, or B elements. Now there's no typos here with the B's. It really does start with a 3, and there really are 3 columns that use 8. Obviously, this scheme is less clear to some than it could be. So here's my first gift to you. Worry about knowing where the taller columns are when numbered 1 through 8, like I have it here. I'm not worried even that you use A in your numbering. If I need to talk about the elements in the middle area, I'll word it something like the element found in the 3rd row of the transition metal block. At least one of you is exasperated by the use of my transition metal block on the last slide. Have faith, my dears. I got you. You just got to give me a minute. We can take groups of groups or groups of columns on our table and organize them by super duper general properties. To make this convo a little less crowded, I'm going to work with an outline of my periodic table. Now, the first and simplest division of our table is between those elements that exhibit metallic properties and those elements that do not exhibit metallic properties. These guys are pretty aptly named metals and nonmetals. Notice that there are a whole lot more metals than there are nonmetals. The nonmetals are only those elements found above and to the right of the stairstep, shown here in red. The elements that lie directly on the stairstep are technically called metalloids. They exhibit some of the behaviors of metals and some of the behaviors of nonmetals. But if you simply group your elements as metals and nonmetals, that will be sufficient for me. The taller columns that we saw earlier numbered with A's comprise what are called the main group elements. These are also often referred to as the representative elements. They include the first 2 columns on the very left and the last 6 columns on the very right of our table. This block includes a lot of the first elements that were classified. The groups in this block do what groups are supposed to do, exhibit very similar and predictable properties to the other members of the group. The overwhelming majority of the chemistry that we discuss in this course and in 117 will involve the main group elements. Now, the elements found between these two sets of main group elements are called the transition metal elements. Transition metals are very widely used, and you'll see them quite a bit, though way less than the main group elements. These properties are less predictable in the area of the table, and a lot of these elements do things that the main group elements simply can't do, such as form multiple ions. These elements even get their own naming rules when we name ionic compounds in the nomenclature module. Now, your last big block of the periodic table are going to be your rare earth metals, often called the intertransition metals. Remember earlier that we said that this block really belongs in the table and that the blue and the bigger part of the green shifts to the right, so the intertransition metals should make sense. Individually, these rows are referred to as the lanthanides and the actinides, based on the first element that appears in each row. These guys are not at all willing to play in the sandbox with others. They do their very own, very different, and sometimes very complicated chemistry. Most of what they do is well beyond the scope of a Gen Chem course. We'll see them from time to time, but we're not going to talk about these guys in any detail. One last quick thing to point out about our periodic table, specifically the color version of it that you have access to. You'll notice that the elements are given in one of 4 colors. These colors describe the state of matter of that element under standard conditions. Think room temperature and just atmospheric pressure, and that'll get you close. Most elements are going to be given in a black font. These elements are solids under standard conditions. There are 10 elements that are included in red font. These guys are gases under standard conditions. There are only 2 elements, bromine and mercury, that are included in a blue font. These elements are liquids under standard conditions. The remaining elements are given in a gray font. All elements with atomic numbers greater than 93 and a number of our other heavier elements are unstable under standard conditions. Most of these either don't exist very long, or we haven't made enough atoms of it to know what state of matter it's actually in, or for them to be studied in any other reasonable way. You'll need to keep the state of matter of an element in mind all term. If you're asked to balance an equation that involves elements reacting, you'll need to include states of matter for that reaction to be correct. You'll be expected to know those states of matter based on this table.